One, this 11.4, here we'll be discussing comparison tests. And yes, tests plural. There are actually two types of comparison tests. The first one is legitimately called the comparison test. The second one is called the limit comparison test, which we'll actually see afterwards. But for right now, let's just focus on this. So here, let's first suppose we have two series, 1 over a sub n and 1 over b sub n, of positive terms. So a sub n and b sub n are each greater than 0 for all n, okay? And the following two conditions hold. So if the series b sub n is convergent and a sub n is less than or equal to b sub n for all natural numbers n, then the series a sub n is convergent. Conversely, with 2, if b sub n, the series of b sub n is divergent and a sub n is greater than b sub n now, then that means the series of a sub n is divergent. I know it sounds like a little bit of overload of information, but really what it says is something that we've actually kind of seen with comparison tests from chapter 7.8 when it came to improper integrals. And it's the main idea, the big basic concept here behind the comparison test is that if you have a series, let's call it S, just S, let's say, and it is bigger than something that diverges. Now, first off, if all your terms are positive, there's no alternating sums. So what that means is that if it diverges, it would diverge to infinity. So if it is bigger than infinity, then this implies that S diverges. So S for sum in this case. If S is less than a finite number, then it can't be infinity. It has to be a finite number as well, because again, there are only positive terms. So this implies that S converges. And that's basically the big idea behind this. So in order to prove we're divergent, we need to be bigger than a divergent series. In order to prove that we're convergent, we need to be less than a convergent series. So that's really all this says once you have things sorted out. So here we're going to determine convergence or divergence for each of these. And actually, you know what? This should be +1. That was a typo on my end. If it was just 1 over 2 to the n, that's just geometric. In fact, what this reminds us of is that it's 1 over 2 to the n. Now, what I'm about to show you will actually be applicable to both of these, and it's a very common technique used in this section. And basically, we're looking at the denominator only, and we want to compare the denominator to something that doesn't have all of this other junk. So imagine just 2 to the n. So how does 2 to the n plus 1 compare to 2 to the n? Well, clearly adding 1 will give you a greater number, and of course 2 to the n and 2 to the n plus 1 are positive terms for all n. So okay, this is fine. But now we don't have 1 over 2 to the n, so what we do is we reciprocate. Since we have positive terms, when you reciprocate both sides of an inequality, let me write recip for reciprocate, what happens is the inequality symbol flips. And I possibly have used this before, but this idea should make a lot of sense. If you have, for instance, 3 is bigger than 2, when you flip them, 1/3 is actually less than 1/2. So this actually compares to 1 over 2 to the n. So we can say that this is less than, I guess less than or equal to, if you want to not think about it too much. The series as n goes from 1 to infinity of 1 over 2 to the n, and we know this converges by geometric series. In fact, if you want to figure out what it converges to, we actually know this converges to 1. We saw that before. So I'm just going to erase this just to show that. So we know this much is true. We know this equals 1. So this series must be less than 1. Doesn't really matter what it's less than. Just as long as it's less than something that converges, then this will imply by comparison that the sum from n equals 1 to infinity of 1 over 2 to the n plus 1 converges as well. Because again, it's less than a finite number, all of the terms are positive, so it's only going to get larger and larger. The sum, that is, only going to get larger and larger. And since they're all positive and the sum is less than 1, it can't break through 1 and go towards infinity, so it can't be divergent, in fact. Good. Now for 2, exact same idea. So if we get rid of all the other junk and just look at, in the denominator for the largest power, it's 2n squared. So we can actually compare this to 2n squared. In fact, you can just compare it to n squared, I believe. So the denominator here, 2n squared plus 4n plus 3, is bigger than or equal to n squared. And you can check that by plugging in numbers, but this is certainly true because since all the terms are positive here, adding 4n plus 3 will only make this bigger than 2n squared, and 2n squared is always going to be bigger than n squared when n is going from 1 to infinity. So this makes sense. And now when you reciprocate both sides, well, you'll get that this is less than or equal to the sum from n equals 1 to infinity of 5 over n squared. Now the reason why it has that 5 is because 5 is a constant. So if you imagine pulling the 5 out, it'd be 1 over. In fact, a better way of thinking of it is just reciprocate both sides to get this. And then just multiply through by 5. So I think that's pretty easy to see. Once you multiply through by 5, then you get that each term in the series is less than 5 over n squared. So the whole series is less than or equal to the series over 5 over n squared. And this converges by p-series. Now again, we don't really know what it converges to. All we know is that it converges. Unlike over here, we actually knew that it converged to 1. But for comparison, we don't care what it converges to, just as long as it's convergent. Good. So we have a series is less than a convergent series. So that means that series must be convergent because all the terms are positive, of course. So by comparison, our series from n equals 1 to infinity of 5 over 2n squared plus 4n plus 3, you get the idea, converges. Awesome. Good. So now we'll take a look at a few other examples. And in fact, we have to see one, of course, where it doesn't converge but diverge. So let's take a look at those examples right now. All right, for this next set of examples here, we were asked to test for convergence or divergence like usual. By the way, just for shorthand, I'm going to use this abbreviation for convergence and this abbreviation for divergence. I've used it from time to time throughout the past few videos, but I'm just going to use it as a standard from now on, just so I'm not writing too much. Now, so these are pretty advanced problems, I'd want to say, especially for something like the comparison test. But I think we can still make do. In fact, this one kind of scared me at first glance because sine alternates in sine. But sine squared, all the terms are positive. So that's okay. The only real issue is that it's not increasing, but I never really said they had to be increasing. The only thing I said is that they had to be all positive. That way the sum will actually be increasing. So that's a little difference there, so keep that in mind. So now what I'm going to do is I want to compare this to something that doesn't have sine there. And remember that sine of k, I guess in this case, is always going to be in between positive 1 and negative 1. If you just think of how sine of x works, it has this graph which is bounded by 1 and negative 1. Good. So that means actually when you square sine, well, sine squared would actually then have to be in between 1 and 0. If that makes sense. Because any number in between 1 and negative 1 has absolute value less than 1. When you square it, it'll also be less than 1. Picking any number less than 1 and squaring that will never be greater than 1. And in fact, if we're squaring it, then it's going to be positive always, so we know it's going to be in between 0 and 1. So more importantly, we know it's going to be less than 1. So we can actually right away do this. We can say this is less than or equal to the sum from k equals 1 to infinity of k times 1, which is just k, over 1 plus k cubed. The next thing I'm going to do is get rid of that plus 1 on the bottom by recognizing that 1 plus k cubed is bigger than k cubed. So let me just write down here, since k cubed plus 1 is bigger than or equal to k cubed, then that means their reciprocals must have the opposite inequality. And now all we have to do is multiply both sides by k, and then we end up getting this. Now what's funny is that here there's cancellation, and this is actually just 1 over k squared. So this series is actually less than or equal to the series from k equals 1 to infinity of 1 over k squared, which we saw already is convergent because it's a p-series. So this converges, it's less than, well, the series we're trying to show, test for convergence or divergence, is less than a series that converges, all the terms are positive, so it must also be convergent. Being less than convergent, if all your terms are positive, means you're convergent by comparison. Okay. So now let me clean this up and move on. Right now, so this one we actually showed was divergent in 11.3 via the integral test. But we want to show this by comparison now. So what I want to do is I want to get rid of ln of k. The only problem is, well, ln of k is certainly less than a lot of things, but what I'm going to actually say is that it's actually bigger than 1. And in fact, you can try to plug in a few numbers in your calculator just to get an idea if these things converge or diverge, and then you can figure out which is the best inequality to go with. So I want to say that this is bigger than 1. All right. Now with that being said, well, this will be bigger than, or I guess you could say bigger than or equal to. Doesn't really matter if it's or equal to though. The series from k equals 1 to infinity of replacing this with 1 over k. Now, well, first off, if you go with this argument, just believe me, this is the harmonic series, the p series of p equals 1, and this diverges, and if we're a series that's bigger than something that blows to infinity, then it also must blow up to infinity, so it will also be divergent. But hang on. Do you really believe me that this is true for all k? Because it's not. Now, when k is equal to 1, so we can try for a few, when k is equal to 1, because that's where we start, of course, we have ln of 1, which is 0. That's certainly not bigger than 1. When k is equal to 2, that's ln of 2, which is about 0.69, which is also not bigger than 1. K equals 3, we'll give you ln of 3. Ln of 3 is, I don't know what it is off the top of my head, but I know it's bigger than 1 because, well, 3 is bigger than e, and ln of e is 1. So this most certainly is bigger than 1 finally. We know ln of k is an increasing sequence because the function ln of x is an increasing function, of course, because its first derivative is always positive. You can check that on your own. But I've pretty sure verified that before in the past. So good. So actually, even though this isn't necessarily true for all k, this is actually certainly true for k bigger than or equal to 3. Meaning, technically for this comparison to work, we would have to split this sum up between, well, starting at 3 now. So if we start at k equals 3, of ln of k over k, we would have to pull out the first two terms. Now the first two terms are what? Well, the first two terms are ln of 0 over 1, which is 0, and ln of 2 over 2. And let me try to border this off between the first problem. Okay, good. So now notice, ln of 2 over 2 plus 0 is just ln of 2 over 2. So this, even though it's not greater than this for starting at 1, it's greater than this starting at 3. But notice this is kind of funny. This is just what? Well, this is almost the harmonic series, but it's you need to kind of add more terms for it to technically be the harmonic series. So this is actually the harmonic series minus a few things. In fact, it starts at 3, so we need to take away 1 over 2 and 1 over 3. But that's okay because this still blows up to infinity, and if you subtract a few finite terms, it still blows up to infinity. So in fact, this summation here, this series that is still divergent. So even though the comparison or the inequality we're trying to use here isn't true for all integers, as long as it's true for most integers up past a certain point, then you can use comparison. So that's a fine print of the comparison test. Doesn't necessarily need to be for all positive integers, but just past a certain point, if it's true for, like in this case, for all k bigger than or equal to 3, then we can pull off the trick because we'll just have, well, either it'll be convergent plus a few finite terms or divergent minus or plus a few finite terms. It's still going to be convergent or divergent though, even if you add a few finite terms. So that's kind of the key there basically. Now this one's actually pretty difficult to show. It's not too bad. What I want to do, I'll just kind of like tell you what I'm thinking here. So the denominator and factorial is kind of what we're looking after. So let me just kind of border these off. So n factorial, if you don't know, we'll actually see this a lot later on in chapter 11, is n times n minus 1 times n minus 2 all the way down to 3, 2, 1. So if you want to do some examples, 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial will be 3 times 2 times 1, which is 6. 4 factorial is 4 times that. So it's 4 times 3 times 2 times 1, which is 24. 5 factorial, for instance, would be 120, because it's just 24 times 5. So you can kind of see how that works. And what I want to say is I want to say this inequality is true. I want to say n factorial is bigger than n squared. Now, that's not true for all integers, kind of like this wasn't true for all integers. Notice when you plug in 1, well, you get 1 is equal to 1, so maybe we want this, I guess. But when you plug in 2, 2 factorial is 2, but 2 squared is 4, and 4 is bigger than 2, uh-oh. But when you plug in 3, still uh-oh, actually. 3 factorial is 6, so this is 3 squared is 9, so it's not looking too good, but at some point it actually starts to take over. So notice when you plug in 4, you get 24, here you get 16. When you plug in 5, we're zooming now, because now we're at 120, versus here we're at 25. When you plug in 6, we're at 720, because it's 120 times 6 basically, where this will be at 36. So there are actually a few ways you can show this. Induction comes to mind. We saw an idea using induction in one of the previous sections. You can also say n factorial is bigger than n times n minus 1 times n minus 2. And that's a cubic, and a cubic is always going to be bigger than a quadratic eventually. So that's what comes to mind anyway. So I'll allow you to verify this for yourself, but I'm at least giving you the idea that it's definitely true after a certain point by plugging in numbers. So if this is true past a certain point, then when you reciprocate, you get that this is true. So that means this would be less than or equal to the sum of 1 over n squared. Now, again, where it actually starts off wouldn't necessarily be at 1. In fact, you may need to take away a few finite terms, but I'll allow you to handle the details there. But this is certainly going to be less than this sum, which converges. So by comparison, this actually converges. And in fact, way later down the road in chapter 11, we'll actually see what this converges to. It's pretty nice. It's a very nice result. I'm not going to spoil it, but it's a really, really, really nice result. And now finally we're going to take a look at the limit comparison test, and we'll see how that strengthens our understanding of testing for convergence or divergence. Alright, so here the limit comparison test, or LCT for short, says suppose we have two series, 1 over a sub n and 1 over b sub n, with positive terms, just like we had for the comparison test. If the limit as n goes to infinity of a sub n over b sub n is equal to a number c, where c is bigger than 0 but finite, so less than infinity, then either both series converge or diverge. This is fantastic because we have a way of comparing two series without having to set up some weird inequality. In fact, all we really need to show is this limit is a positive finite number, and then that means the series actually behave the same, meaning they either both converge or they both diverge. They do the same thing. Awesome. Now notice here I'm not writing n equals 1 to infinity anymore. I'm just having the understanding that they're infinite sums. In fact, we don't really care where they start, kind of what we saw before, because those are just finite pieces. As long as it starts at a finite number, then we're okay. Anyways, with that out of the way, let's try to see if we can get something going here. Now, first off, I want to say, so remember, we actually did this, we did a problem like this anyways at the very beginning. We did 1 over 2 to the n plus 1. Now, 1 over 2 to the n plus 1 was bigger than 2 to the n. 2 to the n minus 1, though, is actually smaller than 2 to the n. And if you reciprocate both, we'll see what I'm getting at with this in a second. We get this. So if we were to try for comparison test, we would see that this is bigger than something that converges, but that doesn't mean anything. Now, if you remember comparison test, if you want to show it's convergent, you want to show that it's less than something that converges, not greater than, because infinity is bigger than anything that converges. So with that being said, this inequality is kind of useless. So, but not anymore though, because now we don't need inequalities. Now we can just use the limit comparison test. So we're still going to compare these two, but not with inequalities. So what I'm going to use is this is called a tilde or a twiddle, depending, I guess, what country you're from, basically. But I think they call it different things in other countries as well. But I'll call it a tilde. So this just means that they compare to each other. So they're not quite the same, but they compare in some way. So what I want to do is I don't want to compare these two. I actually want to compare the inside of this, which is the reciprocal. So I actually want to compare 1 over this to 1 over this. So that's really what I want to compare these two. So by the limit comparison test, I want to find the limit of one over the other. And it doesn't matter which one goes on top, which one goes on the bottom. So with that being said, let's find the limit as n goes to infinity of, let's just say this one over the second one. Now, of course, we can multiply top and, by reciprocal to the bottom, and we'll get the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. And if you want to use L'Hopital's rule here, you can. You can also divide everything straight through by 2 to the n. I'll do that. So if you divide top and bottom by 2 to the n, like this, on the top, we'll get 1, because anything divided by itself is 1, of course. On the bottom, if you distribute this division, we get 1 minus 1 over 2 to the n. And in the limit, 1 over 2 to the n will go to 0, so we're just left with 1. So the limit here is, well, it's bigger than 0 and it's finite. And that's all we need. We want a positive finite number as our result. So that means by the limit comparison test, so I'll write LCT, this actually converges. In fact, they both converge. So I knew already that the series of this, so this compares to the series 1 over 2 to the n, which we know converges. So if I'm comparing it to something that converges, then I know the result will be that it converges by the limit comparison test. We just need to show that the limit is, well, it meets this condition, that it's positive and finite. The limit comparison test, honestly, is a pretty beautiful thing, because all we need to do is figure out what we can compare to and then see if the limit works. But the limit needs to work. It all hinges on the limit. So of course, this here compares to the series from n equals 1 to infinity of 6 to the n over 5 to the n, which is this. Here, notice the ratio is 1, so this actually diverges by a geometric series. So we have a hunch that this diverges as well, but we have to take the inside parts and find the limit of the quotient. So let's take the limit as n goes to infinity of 1 over the other. So let's do this one over this one, I guess. So I got 6 to the n over 5 to the n, all over 6 to the n over 5 to the n minus 1. And, let's see, how do we want to handle this? Well, I guess we can multiply top and bottom by 5 to the n. You know what, let's do this. Let's just not get too carried away. I'm going to multiply top by reciprocal to the bottom. So this is the same as limit as n goes to infinity of the top times reciprocal of the bottom. So the 6 to the n's will just outright cancel. And we get this, and 5 to the n minus 1 over 5 to the n is actually, well, you can split that fraction up. And if you split that fraction up, you'll get 5 to the n over 5 to the n, which is just 1, minus 1 over 5 to the n. I don't know if that makes it on the screen, not quite, but I'll just scoot it over a bit so you can see it. There we go. And this, of course, goes to 0 in the limit, so this approaches 1. So that means it's bigger than 0 and not infinite. So finally, by the limit comparison test, this series diverges. And in fact, I'm realizing now, 5 to the n minus 1 is bigger, or not bigger, but it's less than 5 to the n, so its reciprocals will have the opposite. So this will actually be larger than that. So you can actually show this is true by just comparison. But to set up the inequality, that takes a little bit of finessing, and you don't want to risk it because it could be that it is an inequality that won't work out. meaning that the limit comparison test is just so much stronger in general. The only problem is that this limit, sometimes the limit doesn't work out. That's unfortunate. So by the way, that's an inconclusive condition of the limit comparison test. So if we get a limit that doesn't have those properties, so it's not bigger than 0 or finite, it doesn't mean that that it diverges or converges. We can't say anything. So it's just that the limit comparison test is inconclusive. And in fact, in a lot of chapter 11, we'll actually see tests that have that condition of inconclusiveness. So anyways, moving to this. So you can actually, believe it or not, you can pull off testing for this by just straight comparison. But we're not going to do that. We're just going to compare. Now, the question is, what does this series compare to? So the idea I've been trying to give you is you want to ignore all of the other junk in there. So if you ignore the -1s, the +1 and +4, and in fact it's funny because if you look at this, k squared minus 1 is a difference of squares, so you actually get cancellation, which is nice. But I'm not even going to consider that. I'm just going to look at the powers. So, I mean, yeah, this is 2k, but again, I'm not even going to worry about coefficients. I'm just going to worry about the powers of k only. So here, by the way, this should have been k. Oops, okay, that's fine. So comparing the powers, this is k to the 1, this is k squared. So the largest power is on top multiplied to k cubed. Over the largest power is on the bottom, this is k, times k squared. Squared is k to the 4th. K times k to the 4th, of course, is k to the 5th. And notice this cancels, and we just get 1 over k squared, which we've seen already is a p series, p being bigger than 2, being bigger than 1. So this actually converges. So we have a hunch that this converges, but now we need to sort out the limit. So I'm not going to play around with, not going to play around at all. I'm just going to cut to the chase here. So I want to multiply this by the reciprocal of that and take the limit of that, basically. So let's consider the limit as k goes to infinity now of the reciprocal of this, so k squared, multiplied to this. So it hits the numerator like that. Now, I have mentioned the idea of domination before in this class, and that is a very, very, I don't want to say advanced, but it is a pretty fundamental concept when it comes to these kinds of limits, because you don't have to worry about dividing by the largest power. If you want to expand it and do that, you can. But really by domination, since k is going to infinity, this is actually the same as a limit as the larger powers. So the larger power on top, if you ignore all the coefficients and all of the -1s, I guess, you'll have k squared, k squared. So that all multiplies to k to the 5th. On the bottom, you'll also have k to the 5th. If you expand down and look at the highest power, it's going to be a degree 5 polynomial. This is k. Here, the highest power is k squared. And k squared is k to the 4th. K times k to the 4th is k to the 5th. And this, of course, cancels and gives you a limit of 1. And in fact, to be quite honest, we actually do need the coefficient. So the 2 actually makes it, meaning the real limit is 2. But it doesn't matter. We know we don't really care what the limit is. We just care that it's a positive number and not infinite. So, but specifically it is 2. So that means by limit comparison, this series actually converges as well. Awesome. And again, if you wanted to actually set up the inequality, you could do so. It just takes a little bit of time and finessing, like I've been mentioning. Limit comparison is a little more straight up, but again, I can't emphasize on this enough. You need the limit to work out. Okay, so that was it for 11.4. Thanks for watching. I'll see you in the next video for 11.5. It's going to be a lot of fun, just like this was a lot of fun. See you then.